Welcome to the deep dive. If you're like most people, you probably use AI every single day, but the way these powerful models are actually created, the journey from a blank slate to a functional intelligence, it really feels like a black box.
It does.
Today, we're going to crack that box wide open. We're doing a full breakdown of the AI model training pipeline.
And it's so important to do that. People think of it as this instantaneous digital magic, but it is, in reality, a deeply systematic, very intentional, multi-step process.
Right.
Understanding this pipeline is it's crucial. The reliability, the speed, the intelligence of the final AI, it all depends entirely on the quality and the rigor of each stage.
Absolutely. So our mission here is to guide you through these core steps. We want you to walk away with a clear mental map of how machine learning really works. We've distilled it down to 7 stages, starting with step 1, which is always, problem definition, just deciding what you're trying to solve. But our deep dive today will focus on the core technical steps, which are numbers 2 through 7. We're going to take you from raw data all the way to a deployed model. Okay, so let's unpack the first big operational challenge. Once we know the goal, we hit step 2, data preparation. Now, this might sound like simple digital housekeeping, but my understanding is that this is often the single most expensive, difficult, and time-consuming part of the whole project.
It is.
Why is it such a heavy lift?
Well, you've really hit on a critical trade-off there. It's so expensive because it's the foundation. We have a core principle in this field. The quality of your data will impact the model's performance more than any fancy algorithm ever could.
So garbage in, garbage out.
Garbage in, garbage out. It is the most important truth in machine learning. If you feed the AI messy, biased, or just incomplete data, the model you get out is going to be inherently flawed. It doesn't matter how sophisticated your training technique is.
So what are we actually doing here? I mean, what are the specific actions? If I have a massive spreadsheet or, a database full of images, how do I get from that raw information to something a machine can actually use?
It's really 3 deep tasks. First is just cleaning. You're filtering out errors, duplicates, missing values, the obvious junk.
Okay.
Second is extraction. This is where you identify and pull out the relevant features. Think of it like a detective, identifying the actual clues in a sea of information. We're not just taking the raw spreadsheet, we're figuring out which columns, which pieces of information are actually predictive.
That extraction part, that sounds like where the human expertise really comes in, right?
Right.
It sounds less like cleaning and more like engineering.
It is absolutely engineering. We call it feature engineering, and it's often the difference between a mediocre model and a complete breakthrough. You might have 50 different variables, but maybe only 5 of them truly matter. So we have to transform that data, get it all into a numerical or categorical format that the model can actually consume for its training. The whole point is to make sure the AI has the best possible, most predictive input to learn from.
Okay, so once that data is pristine, we move right on to step 3. Model and training technique selection. Now that we know the problem and we have the data, how do we choose the right architectural brain for the job? Is there like a default AI that everyone just starts with?
Not at all, no. The selection of the model architecture and the training technique that goes with it is based entirely on the type of data you have and the specific problem you're trying to solve. You have to match the tool to the task.
So let's break down those 2 main training techniques because they often confuse people. Supervised versus unsupervised learning.
Right, so this choice depends completely on the nature of the data we just cleaned. If your data is labeled, meaning we know the correct answer for every single input, like this is a picture of a cat, this is a picture of a dog, we use supervised learning.
Okay, so the model learns by being told when it's right and when it's wrong.
Constantly corrected, yes. But if the data is unlabeled, if we just throw a bunch of raw information at the model and tell it, find hidden patterns on your own, that's unsupervised learning.
That makes perfect sense. The data itself tells you which method to use. But let's go back to the model architecture.
Yeah.
Can you give us a concrete example, for someone listening in? If I have image data, what kind of choice am I making and why?
Great question. If you're working with something complex, like high-dimensional image data or natural language, you'd almost certainly choose a structure like a neural network.
And why is that?
Because a neural network is just excellent at seeing these nonlinear relationships that a human could never explicitly code. But on the other hand, if you're working with simpler, structured tabular data like a company's sales history, you might just opt for a decision tree or a simpler regression model.
So we're choosing the neural network not just because it's powerful, but because image recognition is inherently messy and nonlinear.
Exactly. The network can handle that complexity efficiently. It's all about fitness for purpose. You don't use a supercomputer to run a calculator app. You optimize.
Okay, so we have our clean, highly engineered data, and we've chosen the right model structure. Now we get to the part that feels like the main event. Step 4, the AI model training itself. This is where the model learns. What is actually happening here mechanically?
Well, this is the iterative workout phase. The prepared data is fed into the model, usually in small batches, and the core mechanical process is it's about calculating the error, the difference between the model's prediction and the actual correct answer.
And then it adjusts itself based on that error.
It uses that error calculation to continually adjust its internal parameters, we call them weights, in a way that will minimize future errors.
So it's not like a single learning event. It's thousands of tiny adjustments.
Oh, absolutely. We have to emphasize this isn't a one-shot deal. The process usually takes several iterations, we call them epochs, and this can take days or even weeks on massive computers. The model just gradually, incrementally improves its accuracy over time.
It's like teaching a student through thousands of flashcards.
It's a very similar idea, yeah. Repetition and correction cycles.
Now, as the trainers, we have control over the environment of that learning, the hyperparameter tuning. These are the tuning knobs that affect how the model learns, right?
Yes, rather than what it learns about the data itself.
So which of these knobs are the most critical ones to get right?
I'd say two really stand out: the learning rate and the batch size. Think of training a model like driving a car towards a target destination. The target is the point of minimum error. The learning rate controls how big the steps are that the model takes as it adjusts its parameters.
And if the learning rate is too high, you just overshoot the target, right?
Precisely. If the steps are too large, the model might never settle on the best solution. It just jumps back and forth across that minimum error point. But if the steps are too small, it takes forever to get there.
Okay, super slow. And what about the batch size?
The batch size dictates how much data the model looks at once before it updates its weights. A small batch size gives you very quick, localized feedback. It can be a little noisy, but it keeps the model highly responsive.
And a large batch size.
That gives you smoother updates, but it needs more memory and might make the model a bit slower to adapt to, the little nuances in the data.
So tuning these is really about optimizing the training process itself.
Exactly. It's often the difference between a training run that finds a great solution efficiently versus one that just stalls out or produces a poor result simply because the setup was wrong.
All right, the model has completed its training workout. We think it's brilliant, but we can't just trust that feeling. We have to move to the checkpoints, starting with step 5, model validation. Why do we need this internal check before the final real-world test? What is validation doing that training didn't already do?
Validation is the model's first real performance review. And it's so critical because it must be done using a separate validation data set. This is data the model did not see during its intensive training.
Okay.
The whole purpose is to catch the classic, and I mean devastating, problem known as overfitting.
Overfitting is a term we hear all the time. For someone listening, how should we simply define that?
Think of it like this. Overfitting is when the AI has essentially cheated on the tests. It has memorized the training data perfectly. It gets 100% on its homework.
But it can't apply that knowledge to anything new.
Zero power to generalize. Exactly.
Yeah.
It completely fails the pop quiz. So validation checks its performance on truly unseen data to expose that memorization problem.
And we use a few specific metrics for that, right?
Yeah.
We don't just look at simple accuracy. We look at things like precision and recall. Why the extra complexity?
We use metrics like accuracy, precision, and recall because they give us different angles on performance, especially with imbalanced data sets. For example, recall tells us basically how often our AI missed the thing it was supposed to find.
Like a security camera missing a thief.
Perfect example. And precision tells us how often it was right when it did make a claim. If it flags something as a thief, how often was it actually a thief and not, a stray cat?
Got it. These are essential trade-offs.
They are. And validation is also the stage where if we spot a problem, say the recall is too low, we stop. We go back and we fine-tune the model's hyperparameters again for better performance before we even think about moving on.
So validation is still an iterative tuning step.
It is, yeah.
Which brings us to step 6, model testing. Okay, so we've validated it, we've tuned the knobs, again, we feel good. But there's still this final exam the test data set. Why do we need this completely separate, final, unbiased step?
Because the validation process itself by its very nature, influences the hyperparameter tuning. I mean, if you validate and then you adjust the learning rate based on those results, you are subtly baking information from the validation data into the model's final structure.
Ah, I see. So it's not truly unseen anymore, in a way.
Exactly. To get a truly unbiased read on how the model will perform in the wild, we need a completely separate test data set.
One that has never been touched by training or validation. It's the gold standard.
It is the final assessment of generalization. This step is absolutely crucial to see how well the model performs on completely new data without any prior influence. Here, we use metrics again, often focusing on accuracy and something called the F1 score.
And the F1 score, that balances the two we just talked about.
Yes, it's a great way to summarize the balance between precision and recall in a single number.
So this is the final hurdle. If it passes this, it's ready for step 7, deployment.
Precisely. Only if the model performs robustly and generalizes well on this final, unbiased test set is it deemed reliable and ready to be deployed to the user, where the real-world learning and the real challenges truly begin.
And that concludes our deep dive into the AI model training pipeline. We began with problem definition, and then the meticulous high-cost work of data preparation and feature engineering. We then chose the right model architecture, moved into the iterative workout of training, adjusting those crucial learning rate and batch size knobs, and finally, we reached the separate critical checkpoints of validation and unbiased testing.
And we've seen that it's just a systematic and highly rigorous process. Every single one of those stages, from ensuring you have the best possible input all the way to achieving a robust generalization in the final test, plays a critical role.
And that concept of generalization, the model's ability to apply its learning to totally new information, that really is the highest bar we set. And it brings up a final provocative thought for you to consider based on that distinction between the test environment and the real world.
Right. We assess a model by making sure it performs well on a test set. And that test set is data it hasn't seen, but it still comes from the same, let's say, distribution as the training data.
Okay.
But what happens if a model performs perfectly on that test set, gets a perfect F1 score, but then 1 month later it encounters real-world data that is fundamentally different? Maybe there's a huge shift in user behavior or a novel security threat that just didn't exist when the model was trained.
The final challenge isn't just accuracy on data that looks familiar, but achieving true robustness over time in a world that's always changing. So, what are the engineering implications when a generalized AI meets a truly novel scenario that none of its 3 datasets, training, validation, or test ever prepared it for?
That's what we'll leave you to mull over. Until next time, keep diving deep.